Implementation of segmentation techniques in Matlab. This presentation explores image segmentation techniques, their implementation in Matlab, and their applications in diverse fields. Segmentation is a fundamental task in image processing that involves dividing an image into meaningful regions or objects, laying the groundwork for various image analysis tasks. Introduction to image segmentation. Definition. Image segmentation is the process of partitioning an image into multiple segments. Each segment represents a distinct object, region, or area of interest based on properties like color, texture, or intensity. It's like separating a complex scene into individual components. Importance. Segmentation plays a crucial role in various image analysis tasks, enabling us to understand and analyze images. Its applications span diverse fields including medical imaging, object recognition, autonomous driving, and more. Thresholding techniques in Matlab. Basic thresholding. This method sets a threshold value and classifies pixels as either foreground or background based on their intensity. It's a simple yet powerful technique for separating objects from the background. Adaptive thresholding. This technique considers the local properties of the image, adapting the threshold value based on the surrounding region. This improves segmentation accuracy in images with varying illumination. Otsu's method. This method automatically determines the optimal threshold value based on the histogram of the image. It's a popular choice for images with bimodal histograms, where the foreground and background pixels are well separated. Edge-based segmentation methods. Gradient-based. These methods identify edges by detecting changes in image intensity. Gradient operators like the Sobel or Prewitt operators are used to calculate the intensity gradients, highlighting edge locations. Canny edge detector. This popular method combines gradient information with hysteresis thresholding to achieve robust edge detection. It's known for its ability to suppress noise and extract strong, well-defined edges. Laplacian of Gaussian. This method uses the Laplacian operator to detect edges, but with Gaussian smoothing to reduce noise. It's particularly effective for detecting edges in images with varying levels of blur. Applications of edge-based segmentation. Object detection and recognition, detecting objects like cars, pedestrians, or faces. Image analysis, extracting features and analyzing texture, shape, and size. Medical imaging, segmenting organs or tumors for diagnosis and treatment planning. Video analysis, tracking objects across frames. Document analysis, detecting text lines and characters. There are some limitations of edge-based segmentation. Noise sensitivity. Nothing but edge detectors can be sensitive to noise in the image, leading to the false edges. Gaps in edges. Discontinuities in edges can occur due to occlusions or low image quality. Difficulty in complex scenes. Edge-based methods may struggle with images containing complex textures or overlapping objects. Addressing some limitations. Pre-processing. Apply noise reduction techniques like Gaussian filtering or post-processing. Uses techniques like morphological operations to fill gaps and smooth edges. Now, region-based segmentation algorithms. These methods group pixels based on their similarity, forming regions with uniform properties. This is often done by iteratively merging or splitting regions based on criteria like color, texture, or intensity. Region growing techniques start with a speed point and expand the region by adding neighboring pixels that meet certain criteria. It's a simple and intuitive approach for segmenting objects with well-defined boundaries. Region splitting methods, on the other hand, start by dividing the image into small regions and then merge regions that share similar properties. This approach is suitable for images with complex structures. Watershed transformation in Matlab. concept. This method treats the image like a topographical map with pixel intensity representing altitude. It finds the watersheds or lines of separation between catchment basins, representing the boundaries of regions. Implementation. Matlab's watershed function provides a convenient way to implement this technique. It takes an image and a marker image as input, enabling precise segmentation of objects with distinct features. Applications. Watershed transformation is often used for segmenting objects with complex shapes or multiple touching objects, making it a powerful tool for image analysis in various fields. Clustering based segmentation approaches. K-means clustering. This method partitions data points into K clusters, minimizing the distance between points and their respective cluster centers. It's a widely used algorithm for grouping pixels with similar features. Second one, fuzzy C-means. This method allows for partial membership of pixels in different clusters, representing a more gradual transition between regions. It's suitable for images with fuzzy boundaries or overlapping regions. Mean shifting clustering. This method uses a kernel density estimation technique to group data points based on their similarity. It's a non-parametric approach well suited for images with varying density distributions. Level set segmentation technique. Uh, some segmentation. Once the clustering algorithm has grouped similar pixels, each cluster represents a distinct region or object in the image. Assign a unique label to each cluster to identify the segmented regions. The first one, active contours. Level set method represent the segmentation boundaries as evolving contours. These contours are active, continuously deforming to fit the boundaries of objects, guided by image features and constraints. Evolution equation. The evolution of the contour is governed by a partial differential equation which takes into account factors like image intensity, gradients, and curvature. This allows for precise and flexible contour adaptation. Applications. Level set methods are particularly powerful for segmenting complex objects with intricate shapes, making them valuable for medical imaging, object tracking, and image analysis. There are some applications of clustering algorithm. Medical image analysis, segmenting organs, tumors, and other anatomical structures in medical images. Remote sensing, classifying land cover types such as forests, water bodies, and urban areas. Object detection, identifying and localizing objects in images such as cars, pedestrians, or faces. Image compression, reducing image size by grouping similar pixels into fewer color codes. Some advantages: simplicity, relatively easy to implement and understand. Versatility, can be applied to various image types and features. Automation, can be automated to process large data sets. There are some limitations. Sensitivity to initial conditions. K-means clustering, for example, can be sensitive to the initial choice of cluster centers. Difficulty in handling complex images. Images with complex textures or overlapping objects can be challenging to segment accurately. Evaluation of segmentation performance. Accuracy measures the percentage of correctly classified pixels, indicating how well the algorithm matches the ground truth segmentation. Precision represents the ratio of correctly classified pixels to the total number of pixels labeled as belonging to a particular object. Recall measures the percentage of actual object pixels that are correctly classified, indicating the algorithm's ability to detect all object pixels. F1 score combines precision and recall, providing a balanced measure of segmentation performance. It's a common metric for evaluating segmentation results. Some advantages: topological flexibility, can handle topological changes such as merging or splitting of objects. Accurate boundary detection, can accurately capture complex object shapes. Robustness to noise, can be made robust to noise by incorporating smoothing terms in the evolution equation. Disadvantages: computational complexity can be computationally expensive, especially for 3D images. Sensitivity to initialization: the initial level set function can significantly impact the segmentation results. Parameter tuning requires careful tuning of parameters such as the time step and the weight of different forces. Applications and case studies. Segmentation techniques are used in a wide range of applications. In medical imaging, it helps in tumor detection, organ segmentation, and disease diagnosis. In object recognition, it enables autonomous driving, robotics, and facial recognition. These techniques are also used in image retrieval, image compression, and image editing. Thank you.